Alright, today we're going to be talking about polynomial functions and some of the properties that are of them. So, if we read this, this is how we can define a polynomial. Now note, this is probably a little bit more confusing than it really is, so let's just do a couple of examples to show how not confusing it is. So let's say we have the equation y equals to x minus 2. And what is the exponent value of our x term? Well, it's simply that there's an implied 1 here. So that is why we call the degree of this function that we have here right here 1, because that is the exponent value of our x term with the largest exponent value. And if we wanted to graph this, that would just look something like that. Alright. Let's do another example. Let's do an example where degree is 2. So now we just need our largest exponent term to be 2. So we have y equals to x squared minus 2x plus 2. And that is a polynomial degree 2, because if we look at our largest exponent on our x terms is value 2. And if we were to graph that, it would look something like that. Alright, moving on. Let's do an example where degree equals to 3. Say y equals x cubed minus 2x. And if we were to graph this, it would look something like that. Alright, let's do an example where degree 4. We might have y equals to negative 2x to the 4th minus 4x squared plus x minus 1. And that's a polynomial degree 4 because the largest exponent value on our x term is 4. And if we were to graph that, it would start in the lower left hand corner and end in the lower right hand corner. Alright, let's do one last example. So if we have degree 5, maybe we have something nasty like y equals to x to the 5th minus 7x to the 4th plus 14x squared minus x minus 5. Well, on this big old nasty thing, the only thing we need to pay attention to is to the value of our exponent. That is the largest exponent value of our x terms. So, we were to graph this, it would start, let's make this a negative x to the 5th. That's going to start in the upper left hand corner. And end in the lower right hand corner. Alright, so I want to take notice something. These three examples here, the degree of all three of these polynomials is odd. Degree 1, degree 3, degree 5. And notice that our function starts in one corner of the graph and ends in the opposite corner of the graph. This one starts in one corner of the graph and ends in another corner of the graph. And this third example, it starts in one corner of the graph and ends in the other corner of the graph. That is a property of polynomials that have an odd degree. Where if we look at these two examples here, where the degree of both of these polynomials is even, degree 2, degree 4, note that we start in the upper left hand corner and we end in the upper right hand corner. Here we start in the lower left hand corner and we're going to end in the lower right hand corner. So that is just something that's going to be worth noting. So when the degree of a polynomial is even, it's going to start in, maybe it's going to start in the upper left hand corner, then a bunch of things are going to happen in the middle, and then it'll eventually end up in the upper right hand corner. So or maybe it'll start in the lower left-hand corner and it'll eventually end in the lower right-hand corner. And who knows what happens in the middle? Well, right now we're not really interested in that much. It's just that at the extreme values of x, they're going to end up approaching the same value of y, some very large positive value of y or some very large negative value of y. And when the degree of our polynomial is odd, we're going to have a different situation. So that was dealing with even degrees. When degree is odd, we're going to have that going in opposite directions, effect at the extreme values of x. So at extreme values of x, our function is approaching different directions of y. Alright. A rational function is any function that can be written in the form f of x equals n of x divided by d of x, where d of x cannot equal to 0. So just a little notation note, we're calling it n of x because we're talking about the numerator value. So the numerator is a function of x, and d of x will be the denominator, where the denominator is a function of x. And it's important to note that we can never divide by 0, so that's always an important point. So some examples. So we might have f of x equals to 1 over x, where n of x is just equal to 1 and d of x equals to x. Or maybe we'll have another example of a rational function, g of x equals to x minus 2 divided by x squared minus x minus 6, where n of x equals to x minus 2 and d of x equals to x squared minus 6, or x squared minus x minus 6. And note, just a little preview, that when the denominator can possibly be factored, that's probably a good indication that we'll probably need to be doing that. So let's do a third example, where if we just have q of x just equals to 7, where in this case n of x equals to 7, and d of x in this case there is an implied 1 here. So this is 7 divided by 1, and d of x equals to just 1. Alright, so let's talk about the concept of asymptotes. So a vertical asymptote will be a vertical line somewhere where our function would approach that vertical line but never touch it. So that is a property of vertical asymptotes. Our function approaches it but never is equal to it. Same thing with a horizontal asymptote. Will be some horizontal line where a function may approach it but never equal to it. Alright, so let's read these rules right here. Let's read this first one here. If f of x equals to n of x divided by d of x, the number of vertical asymptotes of f of x is at most the degrees of d of x. And we saw for where d of x equals to 0, and this is where our vertical asymptotes are. And dealing with horizontal asymptotes, it's even a little more trickier. Here, if there are horizontal asymptotes, it is most one vertical asymptote. So there's the degrees of d of x would be the most number of vertical asymptotes. When it comes to horizontal asymptotes, there will be at most 1. Alright, if the degree, for the first rule that when we're discussing horizontal asymptotes, if the degree of n of x is less than the degree of d of x, then y of x equals 0 is the horizontal asymptote. So, if we have the function x minus 2 divided by x squared minus 4, Well, the degree of the numerator is greater than the degree of the denominator, so that means that we know that there is going to be a horizontal asymptote at the line y equals 0. No, the line y equals 0 is also the same thing as our horizontal asymptote. So we're going to have some function approaching that value. Alright, the second rule for dealing with horizontal asymptotes. If the degree of n of x is equal to the degree of d of x, then y equals to a over b is the value of the horizontal asymptote, where a and b are both the leading coefficients of n of x equals and d of x. So maybe an example of this where if we have x squared plus 4 divided by x squared minus 9, let's say there's 5x squared plus 4 divided by 2x squared minus 9, just to make things a little bit more emphasize something. So we know that the degree of both our numerator and denominator is the same. So that means the line y equals to a divided by b, in this case 5 divided by 2, where a is the value of the leading coefficient of our numerator and 2 is the value of the leading coefficient of our denominator. So the line y equals 5/2 will be the value of our horizontal asymptote in this example. And then last but not least, for the third rule, if the degree of n of x is less than the degree of d of x, then there are no horizontal asymptotes. So if we have x plus 5 divided by x squared minus 10, the degree of the numerator, which is just 1, is less than the degree of the denominator, which is 2, so that means there are no horizontal asymptotes. So let's look at some examples of rational functions and discuss where there could be possibly vertical and horizontal asymptotes. So let's look at the example. F of x equals to x plus 5 divided by x squared minus 4. So let's go back. Let's deal with the vertical asymptotes. The vertical asymptotes solve for where d of x equals to 0, and this will be the values where we have our vertical asymptotes. So d of x in this case is our denominator, the polynomial of our denominator, x squared minus 4. Now note, x squared minus 4 can be written as x squared minus 2. Oh, screwed up a little bit. X minus 2 times x plus 2. And so where x equals 2 and when x equals negative 2 is where d of x equals 0. So d of x equals 0 at x equals negative 2 and positive 2. So that means we have horizontal asymptotes. Asymptotes at, oh, not horizontal asymptotes. That means we have vertical asymptotes at x equals negative 2 and positive 2. Now note, in this example, we have degree of the numerator is 1. The degree of n of x equals 1. The degree of d of x equals 2. That implies that we have a horizontal asymptote at y equals 0. Horizontal asymptote at y equals 0. Because that is going with this first rule that we have right here. Alright, let's do another example where we have g of x equals to 5x squared plus 10 divided by x squared minus 9. Let's first deal with the vertical asymptotes. Note that d of x equals to x squared minus 9. Then we have vertical asymptotes where d of x equals to 0 at values x equals -3 and 3. Now note that the degree of our numerator in this time is 2. Degree of our denominator is 2. So that means the degree of n of x equals to the degree of d of x. Well, that implies that we will have a horizontal asymptote. Horizontal asymptote at the value 5 divided by, there's an implied 1 there. So that means we have a horizontal asymptote at x, or x, y equals to 5 divided by 1, or that also just equals y equals 5. Alright, and that is following the rule if the degree of the numerator equals the degree of the denominator. That corresponds with rule 2 that we got here. If degree of the numerator is equal to degree of the denominator, then the horizontal asymptote is at the equation y equals a divided by b. Alright, let's do one last example. Let's say we have h of x equals to 100 x cubed plus 5x squared plus 10, all divided by x squared minus 25. And because d of x equals to x squared minus 25, d of x equals to 0 at where values x equals 5, x equals -5. So that means we will have vertical asymptotes at x equals -5 and +5. And looking at the degree of the numerator and looking at the degree of the denominator, in this case the degree of n of x is greater than the degree of d of x. Well, if we go back to our rules, looking at the third one here, if the degree of n of x is less than the degree of d of x, then there are no horizontal asymptotes. And that's what we got going on here. Alright. Take care now.